Welcome to lesson 10.1, solid geometry. We're looking at three-dimensional objects, three-dimensional figures. Our goal, or our learning targets for this lesson, are to be able to classify three-dimensional figures according to their properties, as well as to be able to use nets and cross-sections to analyze three-dimensional figures. A three-dimensional solid figure is a figure that is closed. Again, a figure that is closed, meaning that we have all vertices connected, no open segments, with three dimensions. For example, height, width, length. You've learned about three-dimensional figures from the time that you were in preschool and kindergarten when you studied cylinders, prisms, cones, and pyramids, and just understanding what they were. A face is a two-dimensional surface on the 3D object. An edge is a line segment, has to be a line segment, connecting any vertices on the face, or that connects two vertices on the face. So here we have a three-dimensional object. This looks like a rectangular prism. And this face is two dimensions. This is connecting, this is also a face, it's a side or a face. This is an edge connecting two vertices on the face and the vertex right there. We already know the vertex, I'm not going to define that. A prism is a three-dimensional object with two usually parallel bases and rectangular sides. So they would be parallel bases. This is a prism. One base, this is the base, and the bottom is the other base, and the four sides are rectangles. Or if this was the base, then this would be the base, and then we'd have 1, 2, 3, 4 sides being the rectangles. A cylinder has two circular bases and a lateral rectangular wrap. It could be a parallelogram, but for what we're going to do, it's going to be rectangular wrap or face. A pyramid has one base. It's usually a polygon base. It is a polygon base. It has to have vertices and edges, just like the prism has to have edges. On the cylinder, we don't have any edges. We have circle bases. There's no edges on a circle. The lateral wrap doesn't really have a starting point and stopping point. On the pyramid, we have one polygon base and triangular sides that meet at a vertex of the pyramid, which is across from the base. And a cone is like the pyramid, except it is a one circle base. There are no triangular sides, just a lateral wrap and one vertex. This also has one vertex. The cylinder has no vertices. The prism has many vertices. So on the problems below, we're going to name them according to whether they are prism, cylinder, pyramid, or cone, and the type of base they are. This one, as you might recognize, is a cube. It's a unique one. All the sides are squares. So all edges are congruent. All faces could be bases. They're all have the same area. This next shape, I look at it and it has a base up here that is a triangle and a base down here that is a triangle, and then the three sides, 1, 2, and the back side are rectangles. When it has rectangular sides, it's a prism, and its bases are triangles. So this is a triangular prism. P-R-I-S-M. On the next one, we have rectangular sides, we have rectangular bases, so it is a rectangular prism. On the next one, again, we have rectangular sides, or parallelogram sides, and this time we have pentagons as bases, so it's a pentagonal prism. And this one is a hexagon for its bases, but rectangular sides, 2 hexagons, parallel bases. So we have a hexagonal prism. Down below, because there's only one base for each of these, all of these, and they have a vertex at the top, all of these are pyramids. This one has a triangular base, so it is a triangular pyramid. This one is a rectangular pyramid. Somebody once argued that that was a square. To be a square, you'd have to have the sides marked as congruent as well. This one is a pentagonal pyramid. And this one is a hexagonal pyramid. You name it first by the type of base it has, and then if it has rectangular sides, it's a prism. And it has to have 2 parallel bases. If it only has one base and triangular sides, it's a pyramid. The only other options are cone and cylinder. Classify each figure, name all vertices, edges, and bases. We're going to do this for a couple of the shapes. One of these shapes has only one vertex. If you guessed C, you are correct. That has one vertex. The vertex is N. The base for this one is circle M. We name it based on its center. No edges for a cone. There are sides, it's not really an edge because there's no vertices that are connecting to form the edge. For this one, this looks or appears to be a cube. The vertices are all the letters there, A through H. We put a comma between them. So there are 8 vertices. Those vertices define 1, 2, 3, 4, 5, 6 sides. They're all the same, but I could name them as bases. There are multitude of edges. We have AB, AD. I trace them as I go. AE. My next edge, I'll do some from B, would be BF and BC. My next one would be CG and CD. Then I have GH and DH. I also have FG and FE. And I don't think I missed any, but I have another one here, EH. Oh, you can't see that color. That's supposed to be EH. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges. 8 vertices give me 12 edges on the cube. There are 6 bases. There's not really a specific base. Usually there's 2 and the other ones are sides, but this one could have a multitude, and you name them by quadrilateral. So we'd have quadrilateral ABCD, EFGH, DCGH, AEFB, BCGH. We'd have to have all 6. We'd have to account for all 6. It's a little easier when we get to the pyramid because the pyramid has 6 vertices, the 5 of its base and the 1 above. So the vertices are A, B, C, D, E, F. The base is pentagon A, B, C, D. Notice or E. Notice the 5 letters for pentagon. Notice the commas to separate the vertices. The edges would be all the edges of the base. A, B, B, C, C, D, D, E, A, E. Those are 5. And then 5 more going up to point F. A, F, B, F, C, F, D, F, E, F. So a total of 10 edges. These are the edges. A net is a 2-dimensional representation that would fold into a 3-dimensional shape. That would fold into a 3-dimensional shape. So for example, with these identifying figures from a net, if I make this a base, then this will be a side when it folds up, and this will be a side when it folds up, and this will be a side when it folds up, and this will be a side. This will fold up and have something that can fold down. It'll be the other base. But we know from our exploration that this will be a cube. This kind of looks like the little messenger symbol, little person there. But it's actually a circle base. This edge is going to wrap right around the circle to here. This edge is going to wrap right around the circle to here. This midpoint of this segment, this line and this line are going to meet right on this dot. And this right here will be the vertex of a cone. For the next one, I see 3 triangles, no rectangular sides. So since it has triangular sides, I know it's going to be a pyramid. And its base is a triangle. These 3 will fold up. The top of them will be those points. They'll meet at one point above the center of this. So this would be a triangular pyramid. So that's looking at nets and figuring out what shape it would be. A cross section is like a slice, a 2-dimensional slice. Some of you have been to the deli before where they've sliced cheese or they've sliced meats. And if you have a cylinder of meat and they slice it, then you get a circle if they slice it parallel to the base. But if they slice it perpendicular to the base, draw one, then we end up with lines here and a line here. We end up with rectangles of various different sizes depending on how they slice it. So we're asked to describe this cross section. This one is sliced parallel to the base, so it will be the same as the base. You can even see the edges there. It will be a pentagon, that cross section. This cross section is only at the tippy top, so it is a point. If it were down just a little lower and it were parallel to the base, it would be a circle. This is another cone, but instead of going parallel to the base, they go from the top point and they did straight down. So the edges are right here. It makes a triangle. So the cross section is a triangle. Given the prism with the equilateral triangle for the base, describe how a cross section can make each shape. To make an equilateral triangle, we would have to do perpendicular to the base. So we would have to cross perpendicular to the base. So we'd have to take our slice, our knife, or our rectangular plane, and slice perpendicular to the base. To get a rectangle, we would slice parallel to the base. So if I do parallel to the base, it's going to touch here, 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 and here on the edges, and give us a rectangle. So parallel to the base. To get an isosceles triangle, oh shoot, it says an equilateral triangle. I did this a little wrong. To get a triangle, this should have been parallel to the base because the triangle was the base. To get a rectangle, we should have done we should have done parallel to the edge, parallel to the rectangular edge. I wasn't paying attention. This is a prism. It has 1, 2, 3 rectangular sides. The bases are the triangles. So this was the base. If we do parallel to the base, we'll get the equilateral triangle. Rectangle is parallel to the rectangular base. An isosceles triangle could be an equilateral triangle, just has to have at least 2. So again, that would be parallel to the base. Another option for the isosceles triangle would to be start at this point at the very back and come anywhere along here that's not parallel to that. It will elongate the 2 sides, but the 2 sides would be the same length. The base would just be the original length. This concludes the notes for lesson 10.1. Hopefully this, in conjunction with the exploration, help give you a solid understanding of 3-dimensional shapes. Have a great day.